Hi, everybody. This whole section is on the electromagnetic spectrum. And before we get too far into it, I want to just review some basic wave properties because all of the electromagnetic waves are the same kind of wave. What's different is their size. They go from being very long to very short, and it's because of these different size properties that allows us to use them for different things. Now, all of these are waves. Now, one of the most interesting things about waves is they transfer energy from place to place, not matter. If you are standing someplace talking on your cell phone, it is a cell phone wave. It is a radio wave that is coming, hitting your cell phone antenna and allowing you to talk to friends and family. But it is a pulse of energy that is going through space-time, not even through the air, but it is that oscillating electromagnetic wave. Each wave has a length, and we refer to this logically enough as the wavelength. There's two different common ways to measure it. Sometimes it is measured from the peak or crest of one wave to the peak or crest of another. Another way of measuring it is one complete crest and one complete trough. And these words crest and trough kind of make sense. They're talking about the crest or high point on a wave, and trough just like a trough that a pig would eat out of or an animal would eat out of as a low point in a wave. So one complete wave is one up and one complete down. The symbol that is used to represent wavelength often is the Greek letter lambda. And it is pronounced like that, like the little four-legged fluffy animal lamb, and then lambda. The symbol for it is kind of an upside down Y that's leaning sideways a little bit. Waves also have amplitude. Amplitude basically means how high or how tall they are. And amplitude is a reflection of how much energy a wave has. Now, you may have experienced this if you go to the seashore or a lakeshore and little waves tickle your ankles. They don't knock you over. They're kind of fun to play in, and they don't carry an awful lot of energy. If you go to an ocean where there are big ocean waves and big surf, you can obviously be knocked over, and they can be quite dangerous, and we have to watch out for ourselves and our children in a situation like this. But when we're talking about waves, amplitude is related to energy. So amplitude squared is proportional to energy, meaning if you double the amplitude, you end up with 4 times the amount of energy. Triple the amplitude, you end up with 9 times the amount of energy. So a change in height of those waves makes big waves very, very dangerous. This relates to electrical energy, sound waves, and water waves, and hence big, tall water waves like a tsunami can be very hazardous. Waves have frequency. Frequency is how often. How often does a wave oscillate up and down? We talked about frequency back when we were doing rotation. And when we did that, frequency was number of revolutions per unit time. Well, it's the same idea, but when we're dealing with waves, it's number of waves per unit time. The unit is the hertz. 1 hertz is 1 per second. That top thing is not a unit, but we don't like saying per second. It feels awkward to the human voice, and so we tend to put in something at the top. Sometimes we'll say cycles per second, sometimes we'll say vibrations per second, but that top is not a unit. It is a word that is a descriptor of what's going on, waves per second. You're familiar with it on your radio dial. What you're actually dialing into is going to be a frequency, how often the carrier wave from the radio station is oscillating up and down. FM waves are in megahertz. Mega is times 10 to the 6th hertz. The most powerful and most commonly used wave equation is velocity is frequency times wavelength. And we're going to use this in lab. It is a real handy equation. Velocity in meters per second, frequency in hertz, which is per second, and wavelength in meters. Sometimes you're going to be given frequency and sometimes you're going to be given period. Period is defined as the time for one wave to pass. And the nice thing about these two is if you have one, you can find the other. They are simply the inverse of the other. If you need them, it's nice to have the algebraic rearrangements of these. So let me give those to you so you can write these down. Frequency is going to be equal to velocity divided by wavelength, and wavelength is going to be equal to velocity divided by frequency. Now, the electromagnetic spectrum goes from, as I've mentioned, long wavelengths on this end to short wavelengths on that end. But there are other properties that go along with length as you go from one end to the other. Because of this equation, velocity is frequency times wavelength. As the wavelength gets shorter, the frequency, if you're talking about a wave like the electromagnetic waves that are all traveling at the same speed, if wavelength gets short, frequency is going to get high. So if you have a long wavelength wave, it is going to have a low frequency. So big wavelength, really small frequency, because the velocity of light is constant. You go down to this end, the wavelength is very short, frequency is going to be very big. So that means they're going to vibrate really, really quickly. There's also a relationship between how quickly something vibrates, an electromagnetic wave, and the amount of energy. Low frequency electromagnetic waves have very low energy. They don't pack much of a punch. What does that mean? That means if it hits you or I as a person, they're not going to do an awful lot of damage to us. But if you get hit with a high energy wave, one of these on this end of the electromagnetic spectrum, it could be dangerous. Gamma radiation, overexposure to X-rays, overexposure to ultraviolet light can cause cancer, and so we have to watch out and limit our exposure. I'm going to ask you to do something kind of silly, and hopefully not a lot of people are watching, so you can feel this. I want you to understand this relationship that low frequency is low energy and high frequency is high energy. So on this electromagnetic spectrum, on this low end, we've got radio waves like FM, AM. On the high energy end, we've got radiation, which you probably have heard enough about to know that that can be dangerous stuff. So what I'm going to ask you to do is do something kind of nutty. Take your hand, and what I want you to do is wave it back and forth really slow. Pretend you're like the queen in a parade, slowly waving it back and forth. And as you slowly wave it back and forth, you're going to notice that that's not a really big deal. It doesn't take an awful lot of energy because you're waving at a really low frequency. Okay. Now, what I want you to do is try waving it at a really high frequency, back and forth and back and forth and back and forth and back and forth, really crazy fast. When you do that, hopefully you realize that, holy moly, that took a lot of energy. That is exactly the same idea. If you're going to oscillate anything quickly, you got to put in a lot of energy to make it happen. And that what it also means is if one of these little critters with an awful lot of energy hits something, it can give that object an awful lot of oomph. It's got a lot of energy that it can transfer when that collision occurs. All right, we will come back next time and talk more about the different kinds of waves on the spectrum. See you later.